All around you right now, there's this invisible force that's powering pretty much everything in our modern world. I mean, it's in the screen you're looking at, it's in the motor in your kitchen blender. Today, we're going to pull back the curtain on that hidden force, electromagnetism. And to get started, I want to ask you a simple question. So think about two completely different things for a second. You've got an electric motor, right? A powerhouse of spinning mechanical motion. And then you have a loudspeaker, which creates sound waves. I mean, what on earth could possibly connect those two?
Well, there's the answer. It's not a coincidence at all. They're both built around one of the universe's most fundamental rules, this beautiful and powerful interaction that we call electromagnetism.
So where did this all even begin? Well, to really get a handle on this force, we need to jump back in time, almost 200 years, to a really simple observation that honestly changed the course of history forever. Picture this. It's 1820. A guy named Hans Christian Oersted is giving a lecture, and he's got a wire with electric current running through it right next to a compass. He flips the switch, and all of a sudden the compass needle, which, should only ever point north, it twitches. It moves. In that one little moment, he proved that electricity could actually create magnetism. And what Oersted discovered really boils down to this super important idea. A charge that's just sitting still, well, it creates an electric field around it. We kind of knew that, but the second that charge starts moving, the second it becomes a current, it suddenly generates a magnetic field too. That movement, that's the magic ingredient that connects these two worlds. Okay, so moving charges create magnetic fields. We've got that down. But here's the thing. It's a two-way street. These fields don't just sit there doing nothing. They push back.
And this push actually has a name. It's called the Lorentz force. This is the official term for the force that a magnetic field puts on any charged particle that happens to be moving through it. It's the basic rule of engagement between magnetism and moving charges.
So how does this force actually work? There are a few key things to remember. First, how strong it is depends on the charge, how fast it's going, and how strong the field is. That makes sense. But the second point, that's the weird one. The force always pushes sideways. It's always perpendicular to both the direction the charge is moving and the direction of the magnetic field. And finally, if that charge stops moving, the magnetic force just disappears. It drops to zero. No motion, no magnetic force. Simple as that.
And here's the really wild takeaway from all that. Because the magnetic force always pushes sideways, it can never speed a particle up or slow it down. It only ever changes its direction. You can think of it like you're spinning a ball on a string, right? The string keeps the ball moving in a circle, but it doesn't make it go any faster. In physics, that means the magnetic force itself does zero work. It's just a master of redirection. Okay, so talking about single charges is great for understanding the physics, but if you want to build something for engineering, we need to think bigger. What happens when you have billions and billions of charges flowing together as a current inside a wire? Let's see how that scales up. Well, you get stuff like this, a solenoid. This is honestly one of the most useful tools in all of electromagnetism. It's really just a coil of wire, but when you run a current through it, the magnetic fields from every single loop of that wire add up, and they create this incredibly strong, stable, and super useful magnetic field right down the middle of the coil. It's basically an on-demand, high-power magnet that you can turn on and off. And you see these things everywhere, even if you don't realize it. Solenoids are the heart of those giant electromagnets that can lift cars in a junkyard. They're essential for the transformers that manage our entire power grid. And they're the key to the unbelievably powerful magnets inside MRI machines that let us see inside the human body, all from a simple coil of wire. All right, we now have all the pieces of the puzzle. We know that a current creates a magnetic field, and we know that another magnetic field will push on that current. So let's put it all together and see how we can create motion. This is it, the magic of an electric motor broken down into 4 steps. First, you send an electric current through a simple loop of wire. Second, you put that loop inside a magnet, which then exerts that Lorentz force on the sides of the wire. Third, and this is the clever bit, because the force pushes up on one side of the loop and down on the other, it creates a twisting force. We call that a torque. And finally, that torque makes the loop spin. And if you design it right, you can make it spin continuously, giving you that powerful, useful motion that literally drives our world. So we've seen how these basic ideas build incredible machines.
But let's just take one final step back for a second and appreciate just how profound this discovery really is. It was this brilliant physicist, James Clerk Maxwell, who finally showed with mathematics that electricity and magnetism aren't just related, they are fundamentally the same thing. They're just two different sides of the same coin, a single, unified force, electromagnetism. When things are in motion, you simply can't have one without the other.
So if you take away just one thing today, please let it be this perfect two-way interaction. It's a loop. Moving charges make magnetic fields, and those magnetic fields then turn around and influence other moving charges. The simple little dance is the engine behind pretty much all of our modern technology. I mean, we've used this interaction to light up our cities, to connect the entire globe. But the next big leaps forward, things like quantum computing or fusion energy, they're also going to depend on mastering this fundamental force. The story of electromagnetism is far from over, which just leaves this one fascinating question. What are we going to build with it next?